so now we want to take our fancy new formulas for the scalar projection of u onto v and the projection of u onto v out for a spin. All right, so let's do it. We have u right here, which is 5i plus 15k, and v right here, which is 4j minus 2k. So you want to be a little careful because you'll notice that they don't actually have the same components. U is 5, 0, 15, and V is 0, 4, negative 2. So you want to be careful of that. All right, so now for the scalar of U onto V, that would be the dot product of U and V divided by the magnitude of V. Okay, so the dot product of U and V would be 5 times 0 plus 0 times 4. We're using the ultimate method, of course, because we don't have the angle. 15 times negative 2. And we're going to divide it by the magnitude of V. So that would be 0 squared plus 4 squared plus negative 2 squared. All right, so the dot product is negative 30 over the square root of 20. The square root of 20 reduces down to 4 square root of 5. Oh, excuse me, square root of 4 times 5, which is 2 square root of 5. There we go. And then 2 goes into 30 15 times. So that would be negative 15 over the square root of 5. And if you want to rationalize it, you'd multiply by the square root of 5 over the square root of 5, and you'd end up with negative 3 square root of 5. Now, before I circle that, I'm going to see if Maple agrees with me. So let's go check it. All right, so I have my vector u right here, and I've labeled it u6 because this is example 6, and then I have my vector v. So now I want to find the dot product. So dot product, capital D, capital P, as a matter of fact, of u6 comma v6. And sure enough, it's negative 30, just like I thought. Now, if I want to, I can actually do this all in one. I can say not only find that dot product, but divide it by the magnitude of v6. And it does so. And it is negative 3 square root of 5, just like we said it was. There's the scalar. All right, so we can circle that. We're done with that piece. Okay, so now what about the projection? Okay, so that would be projection of u onto v is the dot product of u and v over the dot product of v and v, or you could just take the magnitude of v squared, that also works, and then multiply it by the vector v. All right, well, we already know the dot product of u and v. It's 30, negative 30, in fact. V and v would be 0 squared plus 4 squared plus 2 squared. And we're going to multiply it by v, which is 0, 4, negative 2. Okay, so this is negative 30, and that's 20. So this is negative 3 halves times 0, 4, negative 2, which would make 0, negative 6, right, because you're multiplying by a negative, and then positive 3. Now, before I go circling that, I'm going to double check myself with Maple, because it's pretty easy to do so. So if I take the dot product of u6 and v6, and I divide that by the dot product of v6 with itself, that does get me negative 3 halves, just like I thought it would. And then if you want, you can actually multiply by v6 right in here. Oops, do lowercase, v6, there we go. And sure enough, it's 0, negative 6, positive 3, just like we said it would be. All right, so we're going to circle that. Okay, for our last example, we're going to look at a classic physics example, which is the tilted block on an inclined plane. Right, it's a sliding block problem. So you want to see if this block is going to slide down this or not. Okay, so we have the vertical vector W, standing kind of for weight, or the force weight, exerted by the object. And that force can be decomposed in two pieces. We have a parallel component and a perpendicular component, which are projections, right? So it's how the parallel projects or how the perpendicular projects onto vector W, which has a magnitude of 100. Okay, so let's talk about the parallel component first, right here. So the parallel component, we're going to need an angle. And luckily for us, they gave us one. They tell us that it's 20 degrees to the horizontal. So we know this angle right here is 20 degrees. Now that also means, right, look, there's a little triangle in here. See that? So that means that angle up there is 70, which means this angle down here is also 20 degrees. And that's going to be great because that's going to help us, right? And then this angle up here, I'm going to give it in pink, is 70, right? 70 degrees and 20 degrees. All right, now how does that help us? Well, again, W parallel, the magnitude of it. The thing about angles like this inside a triangle is that we know how the opposite and the hypotenuse should relate, right? So we know that the sine of 20 degrees would get us the opposite over the hypotenuse. And that would be true for any triangle. And then we just have to multiply it by 100 because that's the magnitude of this triangle, right? That's the magnitude of the hypothesis. So this component right here is 100 sine of 20 degrees. All right, now what about the direction? All right, so direction's a little bit trickier to figure out. It just involves a little bit of geometry here. So I'm going to put my coordinate axes right here. So that's my x-axis, that's my y-axis. And you can see, hopefully, because of what you learned in geometry class, that if this angle is 20, these are parallel lines cut by a transverse. And so therefore, this angle here is negative 20 degrees. Oops, that's a little negative in there. Okay, so that means that the direction of my W parallel would be equal to, well, in order to find direction, I'm not finding the direction right away. I'm kind of using the vector. So I know that it's going to be cosine of negative 20 sine of negative 20. All right, well, yeah, except the sine of negative 20 is the same thing as the negative sine of 20, right? 20 degrees is right up here in quadrant 1. So the cosines would be the same, and the sine would just be opposite. So just because it's convenient, not because we have to, that would be equal to the cosine of 20 and this negative sine of 20. Again, not strictly necessary, it's more just because of convenience. All right, so putting these two pieces together, right, the W parallel is equal to the size of the vector, right, the length, if you will, times the direction. Okay, but the length would be 100 sine of 20 degrees, and we multiply that by cosine of 20 degrees negative sine of 20 degrees, which gets us 100 sine of 20 cosine of 20, and then negative 100 sine squared of 20 degrees. That's the W vector in the parallel direction, or the component of the W vector, if you will, in the parallel direction. Okay, so now what about the perpendicular? Okay, well, the angle for the perpendicular is a little trickier to figure out. So we know that this angle was negative 20, and then that's 70, so that's negative 90 to get us here. And then we can see that that's another 20 degrees right there, right? So this is also 20. Okay, so then putting it all together, that's negative 110. Okay, and then the magnitude of it's pretty easy, right? The magnitude of W in the perpendicular direction, which is this vector right here, is equal to 100, and that's the adjacent side, right? So it's also over here, you can see it. That's adjacent, so it's cosine of 20 degrees. All right, but the direction's going to be a little bit more dicey. We're going to have to use a little trig here. And again, not because it's strictly necessary, it's just to make the formula work out nicer, that's all. Okay, so we can tell, chugging along, that's negative 110 degrees. So this would be the cosine of negative 110 degrees, comma, the sine of negative 110 degrees. Okay, but let's put a little bit more work into that. So on the back side, right, if I go the other direction, that's 70 degrees, right? So, and I can see that I'm just heading in the opposite direction, right? So the cosine and sine will be negative. So this would be equal to the negative cosine of 70 degrees and then the negative sine of 70 degrees. All right, well, that's all well and good. It's fine and it works, but I want to make it even cleaner just for the sake of what I'm about to do. So I'm going to take it one step further. Okay, for this piece, I want to take us back to our pre-calculus formulas. These are trig formulas from a trig cheat sheet that you might have seen in a previous course. And down here in the bottom corner are some identities that we never really spent too much time with. Oops, let me get them zoomed in real quick. They're called the cofunction identities. They're there. So you can see that the cosine of pi over 2 minus theta, say like 70 degrees, 90 take away 20, would be equal to the sine of 20. And similarly, the sine of 90 take away 20 would be equal to the cosine of 20, right? So that's a cofunction identity. So from trig class, you should have seen them in pre-calc, but you probably, it wasn't a big deal made out of them. All right, but now we're going to use that cofunction identity because it's going to help us. So we're going to say, oh, okay, so 90 take away 20 is 70. So this is the same thing as negative sine of 20 degrees. And then negative cosine of 20 degrees. Hello, cofunction identity, right? So it has to do with the way that 90 and 20 are complementary angles. That's why it's working that way. So they're complementary angles, and therefore the cosine and sine work out with those identities. Okay, so we have that. Isn't that great? So now we can put it together. So the W for the perpendicular, or the component of W in the perpendicular direction, is equal to, and we're going to do the same thing. We're going to multiply the magnitude of the perpendicular direction times the direction. So that would be 100 cosine of 20 degrees times that vector, negative sine of 20 degrees, negative cosine of 20 degrees. All right, and that makes it so that it's negative 100 cosine of 20 sine of 20 degrees. If you want, you can put parentheses there, comma, negative 100 cosine squared of 20 degrees. That's why we were using the cofunction, is to make this work out like that. So that's the component of the W vector that's in the perpendicular direction.